Give it a minute. It'll come on.
All right, this is a presentation I did at the recent Safety at Sea seminar, and had about twice as much time, so I'm going to give you too much information and not enough time, and if the projector actually comes on. All righty. Okay, a little bit of wave terminology and theory. The wave theory is all based on sine waves and their rhythmic curve, which would be described by a circle rolling along with a point on that circle. The wavelength, of course, is the distance between peaks. Wave height is from the trough to the top of the crest. So if you're, say, 10 feet off off the water level, when your eye level is 10 feet off the water level, when your boat's floating in the trough, and you're seeing the top of a crest, level with the horizon, that's a 10-foot wave. The period is the time in between wave crests. That's going to be an important thing to remember. And the other thing is that a wave looks like a big pile of water moving across the surface of the ocean. It's not water moving. It is pressure only moving across the water. And that's very important to realize. It's, like if you hear noise, you hear sound, like all those people in the back there, it's not wind hitting you, it's just a pressure vibration. A string on a musical instrument vibrates, the string is not moving along. So the particles of water are just bumping into one another, translating the pressure over to the next particle, and they hardly move at all. So if you watch something on the surface of the water, it floats up and down, it doesn't translate. Until the wave breaks, and that's what makes the breaking wave dangerous. Okay, so we got one nice even sine wave over the top. You add another one at a different frequency. You put the two together, and all of a sudden you've got this beat phenomenon. Big waves, small waves, big waves, small waves. And that's where the whole bit about every 10th wave is the big one, or every third wave is the big one. It's all about frequencies that are piling on top of one another. And of course, waves are formed gradually. You start with little ripples that are created by the water pushing on the wind pushing on the top of the water. Those gradually get bigger and bigger and combine and go faster. So when you combine a bunch of them, here's only three waves put together, makes this crazy pattern. And these ones are all coming in the same direction. So you can imagine the surface of the sea. You've got wind angle changing, you've got wind strength changing all the time, and that's why the surface of the sea looks totally confused all the time. Different wavelengths, because some of them are newly formed and others are a little older. So this is where, the terms sneaker waves, and you get a whole bunch of waves crossing each other, and every once in a while they all pile on, the crests all pile together, and that's a sneaker wave or a rogue wave. It's just a big wave that's very brief usually, and they are out there. I've been hit by several. The oceanographers talk about waves statistically because they are such a big mix. There's a lot of there's short frequencies, there's long frequencies, there's big waves, little waves. So you have to turn it into a statistical problem. And what's important is what they call the H/3 wave. It's the significant wave height. And what that is if you ignore all the little waves and the top the top third of the highest waves are the ones you pay attention to. You average all those, and that's the significant wave height. So, unfortunately, when we're predicting wind, we don't usually know what the significant wave height is going to be because that's observed conditions. So we'll talk a little bit later about what you see when you check in for a wave forecast. But significant wave height, say you have a 10-foot significant wave height reported, the maximum wave height that's possible in that sea state is 2.2 times that height. So that thing doesn't come along very often, but it's possible. And that's what nails you. You see it, you've got a 10-foot wave you're expecting, all of a sudden here comes a 22-foot. Wow. So, okay. So you may have noticed that those sine waves don't look anything like the waves that we see out there. So why don't they? It's the theory that creates the sine waves. But what really happens is you've got wind, which is, water is 836 times denser than wind, than air. So you can imagine, it's amazing really that it creates a wave at all. It's this light thing, it's all the friction of the wind pushing on the surface of the water. And that's why it makes it a long bank and it tends to blow the top off. You get a little tiny cresty thing up at the top. And the face on the back side is a little steeper, on the front side rather. It's approaching you. And the wind will blow over the top of that and back eddy. So the waves grow. They start with little ripples. They get a little bigger all the time as wind blows for a longer duration. Fetch is the distance that it's had a chance to blow over. The two of those combined are what builds the wave up to a fully developed sea, it's called. So when the wind is blowing, it's trying to make the waves go faster. Eventually, the waves catch up with the speed of the wind. That's a fully developed sea. And in that wind strength, the waves are not going to get any bigger, but they do continue to combine their energy. And as the wave gets, as they combine, the more energy, more power, waves are always faster when they are longer. So the distance between crests is the wavelength, and a wave that is long is much faster than a wave that's short. And so if you have a period of 6 seconds, multiply by 3, and that will be the speed of that wave in knots. So a 6-second wave, which is very common around here, there's 6 to 7 seconds, it's a really common wave period. Okay. 6 to 7, yay! I felt like I was yelling. 6 to 7 second period around here is very common. And, if you're on a boat that's doing 16, 17 knots, every once in a while you catch a wave and you'll stay on it for a while. If you're on a boat that's doing an average 20 knots, you'll find you're running in the back of the waves out there. So a swell, we're going to talk about swells here in a moment. The swell period ranges generally from 6 to 16 seconds. That's sort of a definition of swell. So that means you multiply by 3 again to get speed in knots. So a 6-second period means the waves go at 18 knots. A 16-second period means 49 knots. It's not exactly 3. So, again, here's the wind blowing on the wave. They speed up. Eventually there's swell. traveling faster than the wind until it gets really windy. The longest swell ever recorded at a period of 22.5 seconds, speed of 68 knots. So that's slower than a hurricane, obviously. And so that's why you get in really nasty high winds. The swell don't look round anymore. The reason that the swell look round and like a wave, sine wave theory, is because the wind is no longer pushing them. They're smooth now because they're not being, they don't have that shear force of the wind pushing the head off. But when you get in a very high wind, all of a sudden the swell gets nasty again, and that's why the tops blow off them and you get the streaks of foam across the water. Okay, here's the familiar Beaufort scale stuff. Very common condition out here is force 5, force 6, wind speed of 17 to 21 knots is force 5, 22 to 27 knots force 6. So that's really common stuff going on with the Farallones. So the fully developed sea is going to be, a 21-second period, 21-knot wave is going to be doing 7-second period. And you can see the wave down here. It's kind of what I was talking about. These are swell, really, but the wind is just blowing the tops right off. Okay, here's the same Beaufort scale again, but I've added my own stuff over here on the right side. This green region is the typical swell period. So this is a period of when the wave is matching the wind speed. So anything that you're in the light air and stuff, it's a very quick period. 6 to 7 seconds, as I said, very common stuff. In fact, if you think of when you go to a beach, watch the water wave hitting the wood, it's sort of like it's about 6 seconds. All very common. And again, you get down into force 10 and 11. Now the swell is slower than the wind. That's what makes it so crazy. Okay, here's another something I've talked about a few times, but why does a log always come into the beach sideways? This is what I call the log effect. And the problem is that a boat in the waves is stuck between it and the trough. The bow is always wants to shove down by the wave front, and the stern shove the other direction. So that as soon as you lose way, as soon as you are not able to sail over the top of the wave, the wave's too big, you can't get over the top of it, or you lose your rudder, or you're a power boat and the engine breaks, the boat's going to turn broadside to the waves. And so that is one of the number one dangers of lee shore. Get another drink of water with that money. Yeah, I could use a drink. Another wave theory that is pretty common, is true, is that wave length over wave height of 7 to 1 is the maximum wave height. So, as the wave approaches that height, it goes into a peak, and the peak has an angle of 120 degrees. So you can imagine you're trying to pile up water. It's really just a pile of water, and if you get anything steeper than that, it's going to fall over. It's pretty hard to pile water up. So 120 degrees, 7 to 1.